This video is about the quantum mechanical model. You should already be able to describe subatomic particles in terms of mass, location, and charge, and find the number of each of subatomic particles in atoms, ions, and isotopes. In addition, maybe know the general idea of the evolution of an atom. But by the end of this video, you should also be able to construct electron configurations using sublevels, describe the Heisenberg uncertainty principle, describe the shape of electron orbitals, and explain and utilize Aufbau and Hund's rules. So the question of this video is, how come hydrogen forms these specific line spectra? As we saw last year, and we'll see again, hydrogen forms two purple, one dark blue, one teal, and one red line, corresponding to how electrons transition from level to level, energy level to energy level. How come we're not seeing energy transitions that create orange and yellow and green when other elements do have that? So this is one of the major questions that Schrödinger, de Broglie, and Heisenberg were trying to figure out. And they solved all these mathematical equations so you don't have to describe the behavior of electron in the hydrogen atom as being both particle-like and wave-like, which led to the quantum mechanical model. We saw it last year, but we're going to go into more detail. What we're basically saying is that each electron has a specific energy, but they don't follow a specific path as we saw in Bohr. Instead, there are areas of probable electron location, which are called orbitals. The difference is the Bohr had distinct energy levels, or orbits, kind of like the planets around the sun. They follow a 2D orbit. Now we're saying the electrons do not follow such a specific path, and they can be anywhere in a three-dimensional orbital. So a more realistic drawing, they're showing you that there's an X, Y, and Z plane being more like maybe forward and back from you. And they show that the electrons are more probably to be found closer to the nucleus, and as you go farther from the nucleus, you're seeing less and less probability of electrons. Again, this is not a picture of n atom, it's showing you the distribution of where the electrons could be. And they labeled the first electron that they were trying to study the 1s electron. And it led to something called the Heisenberg uncertainty principle. If you see something in red, you most definitely should write it down in case you didn't know. It is impossible to know both the speed and the location of an electron at any given time. You can know one or the other. So it's more probably found in the electron near the nucleus, and the size of the 1s orbital that we just showed you a picture of describes the radius of a sphere, 3 dimensions, that encloses 90% of the total electron probability, where you think you're going to find the electrons most of the time. So these calculations continued until we can describe an electron from any element, and the first number electron configuration represents the overall energy level we saw in Bohr. So Bohr had 7 levels. It also kind of corresponds to the rows of the periods that you see on a periodic table. So if you see a valence electron for hydrogen or helium, it's going to be in the level 1. Valence electrons for lithium through neon are in level 2. Valence electrons for sodium through argon are in level 3. You're getting the general gist, I hope. You're also going to see these letters S, P, D, F. These represent sublevels, or even smaller levels within the energy level, and they also take place in certain regions of the periodic table. So we're going to see the pictures of what S, P, D, and F orbitals look like. They're not necessarily spherical as we saw in the previous thing. That was the overall level. But what you can see is they correspond to these regions. So if you want to block this out on your own reference table, it might be smart. The first two groups, the alkaline and alkaline earth metals, which we see purple here, have valence electrons in what's called the S sublevel. On the right-hand side, you'll see helium is also part of the 1s. That's why some periodic tables move hydrogen and helium in both maybe locations. The green section have valence electrons in a p sublevel. The transition metals and the red section have valence electrons in the d sublevel. And the lanthanide and actinide series on the bottom have valence electrons, or actually higher energy level electrons, in their 4f and 5f sublevels. The superscripts you'll see represent the number of electrons in that sublevel, or maybe if you're looking at the periodic table, the first time you enter that sublevel. So for hydrogen, it's the first row, the s block, and the first electron in. But for helium, it's still the first row, still the s member, because helium's weird, but it's the second one in that sublevel. Each sublevel only holds 2 electrons for s. So you can see that all the alkaline metals have that exponent or superscript of 1, because it's the first time you enter this level. And all the alkaline earth metals have a superscript of 2, because it's the second time we use the s level. You'll notice that there's no more s's left. So we skip over to p. All these have a P1, then a P2, then a P3, so they have similar properties because of their similar electron configurations. We're going to look into why this occurs later, the 4s to 3d switch, why they're not called 4. So hang tight on that. So let's talk about the shapes of these sublevels. So the major level is big spherical mass of where we think the electrons are, but we got a little bit more detail now. We're zooming in into these sublevels. The S sublevel is this orbital that is spherical, just like we thought, but a P sublevel is actually split along one of the planes. So, for example, it's above and below the X plane. It also can be left to right around the Y plane, or front and away from you along a Z plane. Similarly, the D is broken into almost like a clover-like shape, where it's in each quadrant or region of a graph. And F is so complex, we're not going to worry about it for the exam. So what I wanted to look at was magnifications of different S orbitals to see what they look like. The white regions are where we're probably finding electrons, or where they're like, electricity is powerful, and the black regions are where we're not seeing electrons. On the right side, you're seeing the lowest magnification, and on the left side, you're seeing the highest magnification. What it's trying to show you is that the S levels are spherical. And as you zoom in, you see that you cannot have electrons in the nucleus. Same thing with the 2s electron, but the 2s is obviously bigger in size. So at the same magnification, the 2s is larger than the 1s. And as you zoom in, not only can it not be in the nucleus, but there's something called a node, an area where the electrons cannot be. So it can't be anywhere hovering between the 1s sublevel or the 2s sublevel. I always think of it as there's a nucleus, a big black area where the electrons can't be, a ball around that nucleus where they could be, just not in the center, and then almost like a donut, but in 3 dimensions around that outside. So there's an area, a hole, that's in between the inner circle and the outer circle. Remember that we're doing a cross-section here. We're looking at it as if we cut it in half. And the same thing goes for 3s. It's much bigger than the 2s and the 1s. And as you zoom in, you see it can't be in the nucleus. It can't be in the node between 1s and 2s. And it can't be in the node between 2s and 3s. And this goes for p orbitals too. Remember we said there's 3 types of p orbitals. The p orbital is above and below an axis, or maybe it's left to right around the axis, or close and far away from you. See how there's like a couple of different planes that it could be if you cut it in half? In that case, when you look in, notice that 2p starts it. Doesn't start on 1p. There is no 1p on the periodic table. So 2p is where it starts. Again, if you zoom in, you'll see that there's no electrons in the nucleus, and not in between the 2 sides either. So it's on the right side, the white area, and the left side. If you look at 3p, not only is it bigger than the 2p, but as you zoom in, you see, again, a node, which means it could be on the right side or the left side of the nucleus, an area where it can't be, and then another section, that's their 3p. So the inner part's 2p, and this is 3p. And it just is zooming in again, 2p and then 3p. And this is just so big so you can see the nucleus. One more time, 4p. 4p is super huge. So if we go to the zoomed in sections, we can see this was the nucleus where it can't be. This is the 2p, the 3p, and then the 4p on the outside. D orbitals are even more complicated. They're cut in half twice to give you a clover-like shape. I'm never going to ask you about these subscripts, YZ, XZ, XY. I can explain them more in class if you'd like, but it helps us differentiate between the 5. We won't have it on a test, but I will probably talk about it quite a bit in class. So if we zoom in these, they look like a clover. Again, the white areas where they probably could be, and they can be on either quadrant of maybe like this thing of a graph, right? And again, not in the nucleus. And if you look at a 4D, it's much bigger in size. And as you zoom in, you can see this was the original 3D in the first area, and the 4D outside that. Again, you have a node or an area where it can't be. The electrons cannot hover between 3D and 4D. That's where you're getting these jumps in energy levels. That's why you're getting these colors that we're seeing. So let's kind of use everything we learned so far to figure out where the numbered row and sublevel of each of these elements are using the periodic table. Maybe you want to pause the video and then see if you're right. So fluorine is in the second row of the table, and it's in the P sublevel. Carbon is in the second row in the P sublevel as well, because that's why they're in the same area. But manganese is a whole level down. We're calling it 3, and it's in the middle area, so we call it D. I know you probably wanted to write 4D. We're going to talk about that next. Sodium is 3 levels in the S block, and phosphorus is in the 3rd level in the P block. So generally what we're saying is, if you're not really sure what you're doing, maybe you write down this order. This is the order in which we fill electron energy levels or sublevels. As protons are added one by one to the nucleus is the outbound principle to build up the elements, so are the electrons. So like what we're saying is, hydrogen has electrons in the first row, S block, first electron, 1s1. Helium has that electron plus another, so it's still the first area in the S block, but it's the second element in that block. That block is ended, so we go to the next block. Lithium would not just be written as 2s1, but it would include everything before it, so it's 1s2, 2s1. The superscripts up here represent how many electrons are in that sublevel. So for any element, if you add them up, it will give you how many total electrons it has. And if you're talking about an atom, which is neutral, it's also its atomic number. So that's a good check on your work. Let me show you what I mean. So beryllium is found in the second row, the 2s block, the second one in. So it ends in 2s2. But you can't just write 2s2 because a superscript 2 does not represent the fact that beryllium has 4 electrons because it's number 4 in the reference table. So in that case, I had to show everything before according to outbound. It had 1s electrons, 2 of them, and it has the 2s electrons. It's building on the previous parts. Let's do something a little trickier. Sulfur ends in the third row and the fourth one in. So you don't want to just write 3p4 because then it would seem like sulfur only has 4 electrons. You want to write everything that happened before 3p4 in a condensed form. So 1s2 happens, 2s1, 2 happens, 2p, 1, 2, 3, 4, 5, 6 electrons there happens, 3s2 happens, and then 3p4. And so now if you add up your superscripts, 2, 4, 10, 11, 12, 16, sulfur is number 16? Yes, it is. So you know you got it right. How about you pause the video and try titanium? So titanium turns out to be 1s2, 2s2, 2p6, 3s2, 3p4, 4s2, 3d1 due to its location on the table. So some problems we're seeing is the 3d4s issue. So what I was thinking is just try to write the electron configurations in the order of the periodic table, denoting an increase in energy as you go across, which means that the 4s is in fact a lower energy than the 3d levels, though it's still called the valence because the valence is the highest numerical level. So if you look at this, what it's saying is the lowest energy is 1s because it's really close to the nucleus, and then 2s is a little bit more energy because it's further from the nucleus and encloses a larger space. The 2p is even more energy because it's even further from the nucleus, then 3s, then 3p. This is the same order you're seeing on the reference table, then 4s, and then 3d. 3d has more energy, which is why it's written last. Though I'm still going to consider 4s to be the valence because that has a higher number. I would think that maybe 3d is more energy because it has so many electrons in it when it fills up. And then it just goes in order again, 4p, 5s, and then the 4d is messed up again because the whole d block is messed up. Maybe you just want to write it on your periodic table. The d block is one number down. So if we were to write something called the orbital notation, it just kind of shows you where electrons fall. So it says how many electrons in the s level and how many electrons in the p level. It's just a way of drawing or modeling what we're showing. So if you see a 1s2, 2s1 configuration, that means in the one, these are written as boxes, but they're technically circles, right? This circular s has 2 electrons in it, and this circular s has only 1. Or if you go all the way down to something harder, the nitrogen, it has 2 in the first circular s-type orbital, 2 in the second circular s-type orbital, and then it has 3 types of p. Remember, up and down, left to right, and close and far away from you. What they're doing is they're showing how many electrons go in each one. And I'll get into more detail about the up and the down arrows in the next video, but really we're just saying there's 2 electrons. I could have done them as like 2 dots like we did in Lewis structures last year. I could do them as anything I want. I'm just trying to show that there are 2 pieces in that sublevel. Again, they like it boxes because it's easy to draw, but I'm thinking S's should have been circles and P should have been like lobes that we were filling in. So then again, this is just a denotation of how we kind of fill them up. What you might have noticed is that they fill up kind of weird, right? So once you put 1 in the P, for carbon, the next P goes into another block. And for nitrogen, it goes into the third block. So this is something called Hund's rule. It says that the best way we can write them, or in the lowest energy, is to have unpaired electrons. Electrons that are not, in the same boxes. 1 in each box first. So 1 in the X rotation, 1 in the Y orientation, and 1 in the Z orientation. So in English, just like put up arrows if you're going to use arrows, or just know that there's 1 in each box for now. An arrow in each box before any gets 2. So how many electrons that are unpaired for nitrogen? Because we saw before, you're going to go up for P, up for P, up for P. Before you put any doubles up, there are 3 electrons that are by themselves. That's how we think of unpaired. If you don't do it that way, you're going to think it's going to go up, down, up, and you would have only said 1. We're going to prove this by doing a magnetism lab this week. So hopefully that will get a little bit clearer. But for now, just please make sure that if you're thinking about your p orbitals, they are going in an x, and then a y, and then a z, and then they start filling again. So how many unpairs does carbon have? Carbon has 2 in the p, 1 in each box first before we fill anything else. So if you didn't know that we were doing Hund's rule, you might have put them together and said it had 0. But because I split them up, I'm going to say there are 2 alone. Again, I talked about valence electrons quite a bit last year. The valence electrons also correspond to the rows on the periodic table, or the groups. That group 1 has 1 valence and group 2 has 2, and so on and so forth. But if you're looking at a configuration, you have 2 choices. Either you can look at where that element is on the table and then just follow the rule I just mentioned, or you can add up the superscripts of the highest numerical level. So since nitrogen is 1s2, 2s2, 2p3, you add the superscripts for the 2 level, which is 5 valence, which corresponds to group 15. Or for phosphorus, it's 1s2, 2s2, 2p6, 3s2, 3p3. If you add 2 plus 3, you get 5 valence electrons, and that's why they're in the same group 15, because they both have 5. At this point, you should be able to construct electron configurations using sublevels, describe the Heisenberg uncertainty principle, describe the shape of electron orbitals, and explain and utilize the Aufbau and Hund's rules.